theory, as well as for 6 parts of our moduli, is precisely matched with Banach numbers. And that's why our invariants are precisely equal. Okay? And they did something else too, which was really cool, which was they had the construction theory and they made it self-symmetric. So the virtual dimension of their moduli is 0, and they could use this Euler, weighted Euler characteristic formula of computing invariance, the Barron function. The Barron function invariance, though, was not using localization, and the invariance they calculated with Barron function is not the Laplacian invariance. In fact, the only invariance which gives you the Laplacian invariance is the one by localization. That's why their invariance is the same as our invariance. Okay. And the Laplacian invariance by the beautiful paper of Kamran and Witten in 1994, they are predicted to have one property. Okay. So what is the relation between this triple geometry and the Nesta Gilbert disease? Well, it has to do with looking at the 4-6 locus of this moduli of torsion sheet. Torsion means dimension of support of the sheet is less than dimension of the angle. How sheet is supported on the surface. So it has to do with looking at the 4-6 locus of this moduli. The claim is that this guy decomposes into several components who care about several partitionings of that rank R. Remember the Chern character vector with R gamma M? These components care about the partitionings of that rank R. And why is that? Let me show you the analysis in the short time I have, maybe 10 minutes. So remember your non-compact people. This is a projective map on the base surface. You're looking at the 4-6 points of the moduli. This is given by C-star equivariant sheet. And we would like the sheet to be stable. Then what we can do is we can push forward the sheet onto the surface. After all, everything we measured about the sheet, including the Chern character or its stability, is after being pushed forward on the surface. It turns out the push forward decomposes into graded pieces. Okay? So these graded pieces I will call E minus I, or maybe EI if you like. And this thing, I mean, what does this say? This map, this affine map, is the fibers of my line bundle, and the C-star acts on it. So these graded pieces, this T basically here is some trivial bundle on the base surface who have non-trivial equivariant structures that have this C-star weight equal to 1 if you like. And this basically keeps track of what weighted space this EI sits in. So your push forward of the sheet decomposes into weighted spaces E1, E2 all the way of rank lambda 1, lambda 2, as long as the sum of the rank, of course, needs to be equal to the total rank, which is R. So this is how you get different partitioning. So there are so many different ways of dividing a sheaf of rank R on the base surface into directons based on what you choose for these ranks. Okay? And so where's the nesting coming from? Okay, so this is how. Not only you will get this decomposition into weighted spaces, you get something like a Hitchin-type map, or a Higgs map if you like. So those of you who work with Higgs bundles and so on, you know already about this. There is this co-action by the functions in the vertical direction, which actually gives you a map from here to push forward to E times L. Okay, so, and actually if I started just with this Higgs-type bundle or Hitchin pair, the spectral construction would give me back the torsion sheet I have on the people. And the Tanaka story actually is the story of T-side. So they constructed an obstruction theory for T-side. They started from the surface. So if you look at the Mathematical equation, actually you can see that there is some bundle on the base surface, some torsion free sheet on the base surface, with some holomorphic map which takes values 2, 4. It takes values from in endomorphism algebra to in here my Q is lower star of E times canonical. And this is exactly that. The spectral construction gives us the torsion sheet back. So these are some sequels, they also recovered sequels, but they did different obstruction theories. Okay, so the nesting comes from the fact that, remember that this L itself carries a weight, C star weight 1. And each one of the I's fits inside the IT, weight is 6. So because we start from a C star equivariant sheet upstairs, so Hitchin-type map, or the Hitchin pair you get downstairs, also needs to be towards 6. That means the same weighted pieces need to go to each other. So the piece in here, which fits into degree I weighted space, needs to go to degree I weighted space. But then EI cannot go to EI times L because L shifts to degree by 1. The only way you can get maps from same weighted space to the same weighted space is that EI needs to go to EI minus 1 times L. And the stability and so on actually tells you that this map needs to be injected. Remember that these EIs could have different ranks, lambda I and lambda I minus 1. But what if they have both rank 1? Now exactly you get that situation. You have two ideal sheaves, or maybe a twist, and one of them sits inside each other. And the statement is that there's definitely this partition, because you know that this partition 1, 1, 1, 1, 1, 1, how many times exists. So definitely, when you start from calculating the Mathematical invariance, there should be terms coming from this difference. Maybe these corrections are correction terms of 0, but the component of the moduli is definitely there. Okay, because this partition also exists there. Okay, so this is how this story gets related to the Nesta Gilbert. So for simplicity, of course, you can take the rank equal to 2. How many partitions 2 have? Well, you can have only a sheaf of rank 2 with no concentration on the surface, or a sheaf of rank 2 which is really a direction of 2 rank 1 thing, one of them sitting inside the other, and this is this Nesta Gilbert scheme. Okay? The virtual cycle, the localized virtual cycle actually becomes equal to sum of the virtual cycle of each one of these components, and integration against these virtual cycles also tell you that the reduced sound atomic invariance of the sheet will become equal to integral over this virtual cycle, which is this term in here, plus integral against this virtual cycle, which is the Nesta Gilbert scheme invariance. Okay? And it just turns out that this is the moduli space of sheaves of rank 2 seem theoretically supported on the surface. So the statement is that if you have some sheaf whose rank after being pushed forward to the surface is 2, this sheet could be either something which is honestly supported on the surface is rank 2, and those invariants are written either standard Witten invariance and some combinatorial coefficient A, or that this sheet could have rank 1 on the flat surface 2 times X. And the Nesta Gilbert scheme recovers that. Now, I was asked the question from Kamran yesterday, what surfaces we worked on, and this was a great question, and I added this to my slide. So what surfaces we worked on? This S is the final conflict intersection 4K3 surface, which means the condition is satisfied. It's the final conflict intersection of type T1 to decay, 4K3, but this component becomes empty. So this goes away. So this is nice because if someone wants to prove the modularity predicted by Laplacian theory, if they're working on this surface, they need to prove the modularity of the generating series that involves ladder Witten invariance. Okay? Now, if S is a more general type surface, one of these complete intersections, for example, twin in T3, the surface of T3 and T4, or for twin T4, or T2 twin T5, or 2 to 2 in T6, or, for example, blow up of T3 at a point, then it just turns out that you don't need this curve class. This curve class will automatically be deleted, so that your Nesta Gilbert scheme component literally becomes the Nesta Gilbert from a point. You have corrections to Laplacian invariance, but these corrections are coming from Gilbert from a point, which I showed you how to calculate by pulling back class alpha, so on and so forth. So this is our formula again, and as I told you, our invariance, the reduced atomic invariance, are the same as Laplacian invariance. This is our generating theory, we developed, and then Banach numbers with a different obstruction theory turned out they calculated the same numbers using virtualization. Of course, these were different up to a constant. If the surface of K3, the parametric GS is equal to 1, so that's why S is the minus 1. And these are the Laplacian invariants, and both of these are equal to the generating theory of Laplacian in your paper. So this thing actually showed up in your paper, and the equality of these two generating theories is verified after the third coefficient. The calculations are heavy, so that's what I mean 1, 2, 4. But the calculations are heavy, and there was something nice that Richard said in the paper, which is, when you do a calculation that takes 50 pages, and you calculate 3 numbers, each one of which matches with something statistics you hope that, so maybe you actually think that maybe the rest of them should also match. Right. So anyway, so this is after the third coefficient, this verification. And so I need to mention something. These rank 2 sheaf invariants on the 8th surface, these are related to the Saturn-Witten invariants on these coefficients by the result of Mochizuki. So this is not the ABC Mochizuki, this is the Sakura Mochizuki, who's also in the same university, Kyushu. And so some walk-crossing in the master states. And these combinatorial coefficients, this paper also, I think good job actually mentioned it, Gucci and Kuh recently worked out this thing, and they were hoping that they recover the Markov-Witten invariant modularity phenomenon by just looking at this. So this one actually has a very easy generating field, the whole thing not. This is complicated. And he told me actually, he didn't exhibit it here, and he told me that in some cases where the net difference component was definitely there and they were not vanishing, he said we were missing some numbers, and then we realized they were in your components. So, of course, some of the two things need to be modular, maybe not both of them are modular. But I think I would suggest that if you are interested in this, consider those final cases where this goes away and just prove the modularity thing. I think it's fantastic. And this is our necessary scheme. Okay, and this is how ugly these formulas look like, but I don't know, I mean, this particular coefficient A, these are here, these are these A, see, I mean, but Gucci and Kuh have the power of doing this, and they have the nerve for doing this, so they did it fantastic. What happens for R bigger than 2, if the first graph of the sheet after being pushed forward to the surface is bigger than 2, of course, numbers bigger than 2 have more interesting coefficients, so your expected formula is again some Mochizuki confusion, which I believe you can also relate to Saturn-Witten invariance by applying his walk-crossing more than one time. And then you will get definitely the necessary invariance, the bar construction is general, and definitely recovers that, and then you will get the dot. And the dot are these components which have to do with the remaining partitions of the grand car, and there is no virtual cycle theory or intersection theory developed for those, but those are right now work in progress, and I thank you here. Any questions? I didn't know that, thank you, yes, we will check that. Any other questions? Yes. No, definitely. Countdown counting invariance do only will become equal to the invariance of the spool format. For final complete intersection, in case 3 there is no net regression. No, they're not. Other questions? Unless, let me comment something. Unless you fix the Chern character somehow that, first of all, the first class goes away, so this will be one of those 5 complete intersections I gave, by pointing surface in T3, and you fix your Chern character sheet somehow that, the netting of points you get there is somehow that N1 is less than N2 by 1. That is basically smooth. And then you can calculate this point effectively initially. And our theory actually does give us, I put the formula for it, so it's just some formula, right? So. I don't want to be that brave, but I showed it to one of my other collaborators, Yokinobu Soda, and he said this is the DT theoretic analog of that. Holomorphic analog of that, but I'm not claiming such things. I mean, that's a very hard problem. So. Other questions? And the title is Motivated Out Life by the Show. Right, thank you very much. So it's a real honor and pleasure to be able to be here and speak on the case. Right, so it's a honor and pleasure to be able to speak at the 50th anniversary of the Journal of Differential Geometry. And I'll just say I'm proud of the fact that I have 8 JDG papers and so an honor to have those papers here. And in fact, I so finally remember that I was looking for a place to sit my first paper and the affiliations that I noticed that Lane Lawson was editor of JDG, and so I thought, well, maybe he would appreciate this paper. Sorry, so that worked out okay. So I want to talk about the 4-dimensional light bulb theorem. But before I do, let me just mention this, which is that it's about the study of a special case of understanding 2 spheres in 4 manifolds. So here I'm working in the smooth category, and 2 spheres in 4 manifolds. It has a long history. It's an incredibly fascinating subject, and it's really fundamental to 4 manifolds. So I mean, at the very least, I mean, if you're just looking at 2 spheres in 4 space, I mean, it's an incredibly great subject, which is amazing how little is known about that. I mean, for example, there's every group that's a fundamental group of a knot in 3 space is a fundamental group of some 2 sphere in 4 space, and unlike 3 space, where that more or less determines the knot modulo some other things. I mean, it's far from it. For example, there's a basic question is, if you have a 2 sphere in the 4 sphere, which whose complement is fundamental group Z, is that 2 sphere just the standard sphere? And of course, one of Friedman's amazing theorems is, yes, that's true in the topological category, but in the smooth category, it's not known. And in general, in 4-manifold theory, if you have nature of ordism between simply connected to close simply connected 4 manifolds, then if you look at this 5-dimensional H of ordism, multi-action can be put in the middle level, and you can see the ascending 2 spheres and descending 2 spheres, and of course, if you're in 5 dimensions, you can use the Whitney trick to disentangle them, but just understanding these spheres is really central. So here's another case of, just here is meant for more an historical thing. So one of Steve Snail's early spectacular results was Euclidean of the regular homotopy of two spheres into Euclidean space, which he was, was able to turn the sphere inside out. And then later he developed extension of understanding K-spheres and space, and then, well, Mo-Hirsch extending his method to generalize this, so general theory of immersions. But in particular, I mean, Snellius developed an analogous theory for embeddings. Presumably this will be quite hard. Even partial results in this direction would be interesting. So already when you're talking about embeddings, that I mentioned this fundamental group in stochastic psychology because incredibly sophisticated things are involved. So, but what about the question, the basic question, how under what conditions are two spheres actually isotopic? And as far as I know, there's strikingly little known in the subject. In fact, I mean, this, as far as I know, this is really the only general theorem I know of that type in the subject, which is that if you have well, I'm stating this for two spheres bounding walls, but I mean, their theorem is true in all dimensions. But if you just have in fourth space a two sphere bounding a three wall, again, in the smooth category, then that's isotopic to the standard sphere. And the reason simply is that if it's bounding a smooth wall, then you just look at some point in the ball, just look at just a little neighborhood about that, then, well, I guess that's the standard sphere. But on the other hand, since this thing bounds this thing bounds the ball, then you just smoothly isotopic to its, approximately, neighborhood. So it's very close, differentially to the standard thing. So therefore, you can make it a standard thing. So questions of, when are spheres isotopic is strikingly little known. So the Light-Bulb theorem is a condition, as you'll see in a moment, for two spheres to be isotopic. So here's the three-dimensional Light-Bulb theorem. The three-dimensional Light-Bulb theorem says that if you have a knot that's a simple closed curve in S2 cross S1, and that knot it hits the S2 just in one point transversely, then that knot gets to be isotopic to standard vertical curve. And well, I mean, here's the main idea, which is that if you want to undo a crossing, you just slide that piece of knot all the way down to the two sphere. You just send it around the two sphere and just send it back up, so you can just undo crossings. And if there are some number of crossing changes, you can see it's just a standard vertical thing. So the goal of this talk is to explain the four-dimensional version. Before I do that, why is this called the Light-Bulb theorem? So if you have a light bulb hanging down from the ceiling, and the cord is knotted up, then you can unknot the cord without moving the bulb. So, I mean, here, the second cord's stretchy. And you can see that there's a region between the sphere and the ceiling. Well, if that is just, the ceiling's like the boundary of the free wall, and the bulb is the inside. If you glue the bulb to the ceiling, then you get S2 cross S1. So that's why this is sort of really the same problem. So here's the four-dimensional Light-Bulb theorem, which is, well, you have S2 cross S2, and so you have this horizontal S2 cross 0, and then there's the standard 0 cross S2. So the Light-Bulb theorem says that if you have another two sphere, which hits the horizontal two sphere transversely in a point, and here you can gain the same homology class as the vertical one, then in fact it's isotopic to the standard one by isotopy keeping S2 cross 0 fixed point-wise. I should say 30 years ago there's partial results in this direction. Well, I guess Matsumoto, he proved this in the topological category. Actually, he proved something different, which is the most equivalent. And Littlin showed that there is actually diffeomorphism that's pseudo-isotopic to identity, whatever that is. So my goal is to explain this. So one of the challenges is how to think about S2 cross S2 in a useful manner, at least for this problem. And the way we're going to think about it is, well, we have a vision, a picture of how to think about S2 cross S1. The way I think about S2 is horizontal thing, and S1 is a vertical direction. So if we're going to look at S2 cross S2, let's keep the first S2 as S2, and the other S2, think of that as like S1 cross infinity, where you just contract the minus infinity to a point and the plus infinity to a point, right? You just take a long cylinder and just contract the ends. Well, then that's a two sphere. So if you think about it that way, then well, at least except for the end two spheres, you think of that as just a one parameter's worth of S2 cross S1s, which sort of contract to S2s at plus or minus infinity. So here's just a restatement, which is that if we think of the standard two sphere now as G, like think of it as green two sphere, and it's just S2 cross Y0 is point S1 cross 0 is like the time parameter. There's G is the horizontal sphere. Then the vertical sphere intersects every S2 cross S1 is just the standard vertical arc. So the Light-Bulb theorem says that if you have a two sphere that it's just this green dot once transversely the same homology class, then it's like topically standard. So to get started, it's useful to think about what does the neighborhood of this green two sphere look like. Of course, it's obvious what to do in S2 cross S1, just thinking it up, and the natural thing is thinking it up in a little bit in the time parameter too. So I should say, I should go without saying, after all, is that point where our two sphere intersects the green sphere. It just agrees in just some tiny neighborhood with the standard sphere. So it's a little bit, it agrees at this point, and a little bit forward in backward time. But again, it's useful to find out the neighborhood of this green sphere is. And to get a sense of that, it's worth understanding what does the neighborhood of a point in the two sphere look like. So here is the two sphere. Remember, two sphere is a cylinder with the ends contracted to a point. So here I'm thinking about the S1 direction, and the horizontal is the R direction, and then the plus and minus infinities are have this point. So this picture of S2, this green thing is the neighborhood of a point. So once we understand that, then we get a nice neighborhood of G. So, and the neighborhood of G is, well, if we have this thing parameterized between minus 3 and plus infinity, then the neighborhood of G includes everything to the left of minus 10 and to the right of plus 10, and then from between 10 and minus 10 and 10, in that those S2 cross S1 sections, just for a little standard neighborhood of that S2 cross S1. So here's sort of a picture of this, is that the neighborhood of the green sphere is everything to the left, everything to the right of, from T plus figure equals plus or minus 10. So in particular, our sphere that we're trying to understand now looks standard, where the T parameter, time parameter is less than equal to minus 10, or looks bigger than equal to plus 10. And for a generic slice, time slice, well, it's you're taking a three-dimensional slice of a sphere, so it's some one-dimensional manifold, so maybe it looks like that. So I mean, it's multiple zones. But the utility of thinking this way is now we think it has a Morse function where we have, to the left is the standard thing, and then we get to see how, with this T parameter, how the bar changes. So, right. So now we just do basically standard Morse theory where we look at the surface and perturb it slightly to be a Morse function. And so there's slightly many points, critical points in the x0, which we just assume are happening at time minus 9. And then there's the critical points in the next minus 1, which, well, for whatever reason, they could happen next. But so the critical points in the next 1, they happen next. And for whatever reason, that's happening between half of them at minus 6 and half of them at plus 6. And then the critical points in the next 2 are plus 9. So now, writing these are these slightly non-generic. What you think of is that time, before time minus 9, this is the standard vertical curve. At time minus 9, you suddenly see these, some number of disks. And then you just see these boundary circles for times between minus 9 and minus 6. And then at minus 6, you see some bands appear. Those are like the critical points in x minus 1. And then there's bands here at plus 6, and then disks vanishes at plus 9. Now, you just a minor variation of the theme is that, well, the standard vertical curve, I call it the core curve, and so this guy's the core curve, and it's easy to arrange that you have these bands, one ends at the core curve and the other ends at one of the circles, and so if there's n on 2 circles, then there'll be 2 bands at minus 6, just connecting the core circles. So between minus 6 and plus 6, actually the intersections are connected one manifold, and then at minus 6 and plus 6 there's these bands, these circles at 50 over plus 9. So this is the way we're thinking about this. Sorry, the left side. The green. So the green is a standard sphere. So these, I'm showing you 4 time slices. And so the green is really just living at one time slice is equal to 0. But I'm looking at I'm picking it up a little bit. So looking at the regular neighborhood. So the regular neighborhood of the green at these various time slices is just a standard green, just ever so slightly thickened. So that's why these are the x2 cross 0 is just pieces of this regular neighborhood. So again, we have disks here at minus 8 and bands at minus 6 and then other stuff at plus 6. So right. So now if we right. So here's something to me. What if there's no critical points whatsoever? Well, what that means is that at minus 9 you just start with this standard vertical curve, and then this curve is just come out like being isotoped in S2 cross I. Right? It's just standard near the green, so it's what's left is S2 cross I, and as the time parameter changes, you have this curve just moving around S2 cross I, and then at time plus 9 it becomes standard again. So it should be obvious that's standard, but I don't know if I do it. Hit it with a big sledgehammer. So, and that is that if you have no critical points, then this sphere gives rise to a path, a loop in space of embeddings of the interval into S2 cross the interval, where the endpoint's fixed. And by isotopic extension, if you have an arc that's sort of moving around, where you just sort of extend the space. Now, the little technical point is that this loop in the embedding space extends to a loop in diff S2 cross I boundary S2 cross I. And actually, this is how you could sort of do the extension and just string it all the way out to the very end. Actually, this is the point where I use this in the homology class. I mean, after all, it could be in a little different class, which is the vertical one plus some number of copies of the horizontal one. And if within that class, then at time plus 9, you have S2 cross I with some 2n rotations. But you need to sort of isotope that to the standard thing, fixing the core circle, which so anyway, now this amazing theorem of Hatcher, he has these 17 factorizations of the L conjecture, and one of which is that diff S2 cross I boundary S2 cross I is pi 1 of a loose space of O3, and that turn is pi 2 of RP3, which is pi 2 of S3, which is trivial. So therefore, you could use this contraction space of diff to straighten up this curve. So now we can assume that if there's no critical points, then this sphere is standard. Okay, so now let's consider what I consider to be basically the representative case, which shows essentially the main difficulties. And that case we have 2 critical points, 2 of the next 0, 2 of the next 1. And if you make a slight perturbation, you could have, one disk appear at time, say, minus 9, the next disk appear minus 8. And then a band that to kill, associate this boundary curve appears at minus 6, and the next band is pushed up in time to minus 5. So somehow I want to be able to cancel this critical point in the next 0 with this critical point in the next 1. So how do you do that? So first, I'd like to be able to say that right at this level, at this time minus 6, I can find an embedded disk bounding this curve, embedded disk bounding that curve, which is disjoint from all the other stuff. So this disk is everything else except for like the spark. So the question is, how do you do that? Well, abstractly, we have this picture. Here's our two little circles. Here's our band, which just goes all around S2 cross S1, crashes through here a bunch of times. And so I want to find actually replace this disk by other disks, which are disjoint from all this other stuff. So from the band's point of view, is these two disks are just hitting the band in various spots. So what we can do is like look at this first one and just stick your finger and just push it off the band. Well, if you push it off the band, okay, that's fine, but it hits the core curve twice. But I'm not worried about that for the instant. But then that leaves room to push the next disk off, and then the next disk, and so on and so forth. So I replace intersections with the band with intersections with the core curve. But then, again, here's a spot where we're using, that we have this dual sphere. So we can just basically, we have this intersection here, and we have a sphere here, so we just tube off this intersection. And so just take a copy of this green sphere, just push it off a little bit, and just tube it off here. And with this one, just tube it off in the other direction. And once we've done that, well then we've, at least we've just cleaned up this spot and replaced this disk that passed through here by a different disk, but at least it's disjoint from everything. And we can do that one by one and replace all these disks by disks disjoint from other stuff. So that enables us to sort of view time minus 6 with differently. So we can use those disks to just basically straighten up the picture of time minus 6. So just straighten them up. Now, and we can do that because these disks, I call E1 and E2, before they were originally. I mean, they were disjoint from things. So, but now remember that these disks, well, down to these curves, and these curves, well, up to time minus 6, but all the way down to time minus 8 for E1, for down to E1, and minus 5 and minus 9 for E2. Every time slice, they're just sitting there, just like circles. So the isotopy, which takes this, this crazy picture and just straightens it up, I want that to be just carried through the all the various time slices, say between minus. Well, actually, 8.5 here, 5.5. So, right. Okay. So it looks like they're really in good shape because this is really a much simpler picture than what it was. However, we have to pay a price. And the price is that when we did this isotopy, then, remember, at time minus 8, this original little disk here to our critical point at -0. But when we did this sort of isotopy, well, then that took that disk and turned it into a mess. And this is the picture that we can very well see at time minus 8. You see, like, here's a sphere, here's a sphere. So this circle here is tubing to this inside sphere, and down to this little tube that swings around the outside sphere. So you see that this is a mess. And it's this nice straight band. If you push it down to the minus 8 level, it's crashing into this disk. Now, if like a miracle, it was disjoint from the disk, well, then we'd be able just to do a cancellation, but it's not. So somehow we want to make this band disjoint from, so now I just say this band is disjoint from this complicated disk. And just to do that, I look at this curve C2, and I want to disentangle this curve from the tubes that are passing through it. So let's look at just a detail of that. Here's this circle C2, and we saw these tubes passing through. And, well, I mean, you're thinking about this, and late at night, you say, oh, shoot, why don't you just move it off? And then you say to yourself, well, here's a tube, and here's a circle, and just move this a little bit to the fourth dimension and move it back. But that doesn't quite work, right? Because there's this circle here, I'm sitting here at level minus 8, but it's, at every time slices and forward backward time, plus or minus 1, I mean, it's still there, so I just can't reliably move this off.